What's up? Welcome to Wagner Academy. It's time to get excited. Why is that, you might ask? It's time to do some math. Geometry, lesson 2.3, conditional statements. Here we go. Some new terminology for you, probably some very new concepts within this lesson. Make sure you're paying close attention and make sure you use those extra examples in the book to help as always. The first blank for lesson 2.3 is a conditional statement. A conditional statement is a statement that can be written in if-then form. If-then form. So if something, then something. And then this second bullet point, we start off with an if-then statement is written in the form if P, then Q. So remember from lesson 2.2, we had P and Q representing these whatever statements. They're kind of like variables in algebra. They're like variables in logic, variable statements. So P and Q, the phrase immediately following if is called the, and this is hearkening back to lesson 2.1. We talked about conjectures, and I said don't confuse that with hypothesis. So a hypothesis is the part after the if. Conjecture is an educated guess within logic speak. And the phrase immediately following then is called the conclusion. And in symbols, if you have something written like this, P and then an arrow and then Q, some books will have, I wouldn't write this if you're one of my students, but just realize that some books might have something that looks like this instead of this. So a double line instead of a single line. It means the same thing. But both of those things, what do they mean? How do you read that? This is read if P, then Q, if you were reading that out loud. Or you could also say equivalently P implies Q. Those two things mean the same thing. So this can be read if P, then Q, or P implies Q. And example 1, let's see what we got. Identify the hypothesis and conclusion of each statement. So it says up here what we need to know, the part after the if, that's the hypothesis. So this one's in an if-then form already. The if and the then are there. This clearly then should be the hypothesis. So we have, I'm just going to box that in. I won't rewrite it. This is my hypothesis, the part after the if. And the conclusion is the part after the then. So notice I'm not including if, I'm not including and then in these phrases. And I'm also not including the punctuation. It's just the phrase itself. So this is, I'm not saying whether or not this is a true statement right now. I'm just identifying what the hypothesis and conclusion are. So I could consider the truth value of this statement. If a polygon has 9 sides, is it in fact a nonagon? Yeah, that's what a nonagon is. So this one would be a true statement as well. B, the hiking trip will be canceled if it is raining. Lame. Just because of some rain, you're going to cancel a hiking trip? But let's write that in if-then form. Write that a little neater. There we go. Still not the best, but that'll do. If-then form. So I notice the if is over here now, so I'm going to rewrite this with the if part coming first and then the then, and then it's easier to identify the hypothesis and conclusion from there. You wouldn't have to do this necessarily to identify the hypothesis and conclusion, but I think it makes sense to do so. So if it is raining, then the hiking trip will be, and I'm running out of space here, that's okay, will be canceled. I'll write that underneath there. So we have to identify the hypothesis, so that's the part after the if. So this phrase, it is raining, would be the hypothesis. And then this part, the hiking trip will be canceled, that would be the conclusion. So you can rewrite a phrase in if-then form oftentimes, even if it's not in that form or if it doesn't have the words if and then in it to begin with. So hey, here's some people that decided it's fine to hike in the rain. And then this is actually a friend of mine. We both had hiked the Appalachian Trail back in 2005, and then in 2011, this is Jennifer Farr Davis. If you want to look her up, she's actually the world record holder, male or female, for the Appalachian Trail. She hiked the whole trail in 46 days and some change. It goes from Georgia, northern Georgia, all the way to central Maine, and it's about 2,175 miles long. She averaged about 47 miles a day of hiking. She was supported by her husband. He was following along on road intersections. He would provide food and whatnot, and other people helped her out, but she hiked the whole way, all on her own 2 feet, all under her own power. Pretty amazing story. Let's check out example 2 now. So write each statement in if-then form. 2 lines that never intersect are parallel. So I don't see an if or a then in there. However, we can change this. We can arrange this sentence in a grammatically correct way so that it has an if and a then in it, and so that it means exactly the same thing. So we could say something like this: if 2 lines never intersect, then they, since I already have described what I'm talking about, 2 lines, they refers to those 2 lines, then they are parallel. And we could identify the hypothesis and conclusion from there. Doesn't say I have to though, but it would be 2 lines never intersect, the hypothesis after the if. Part after the then, they are parallel, would be the conclusion. Part B, buy 1 phone at full price and get another for 50% off. Wonderful. Don't you love those salesmen that push that on you like that? But how could we write this in an if-then form? Here's one way we could do this. You might come up with a slightly different way you could phrase it, but this is the way I thought of. So if you buy 1 phone at full price, then you can get another for 50% off. Oh, okay, calm down there, Mr. Wagner. For 50% off. But it's got an exclamation point, so there's that. Moving on to the next bullet point. Just as a statement is either true or false, we learned that in lesson 2.2. The hypothesis and conclusion, so it goes in these first 2 blanks, the hypothesis and conclusion of a conditional statement, as well as the conditional statement itself, can also be true or false. So we are going to practice some truth tables again with this lesson. We learned about truth tables first in the previous lesson. We'll have a couple to fill in here as well. So example 3, determine the truth value of the following statement for each set of conditions. So here's the initial statement. We're going to assume this is a true statement. The hypothesis and the conclusion are both true in this statement. So if you are a lawyer, then you make $200 an hour. So we're identifying this part as the hypothesis, and this is true. This is the hypothesis. And we're identifying this part. You make $200 an hour. That's the conclusion. And we're also assuming that is true. So if I look at this first one, okay, here's the conditions. You are a lawyer, you make $200 an hour. Does that satisfy what I see up here? Do I have both parts being true? I sure do. So I've got you are a lawyer. So that's true, because that's the same hypothesis as what I had up here. And then I have you make $200 an hour. And that was the same conclusion I had up here. So this one should make sense, that would in fact be a true statement. If we can assume the initial statement up here was true, this would be a true statement. If you are a lawyer, then you make $200 an hour. Satisfies the conditions I see up here. As we do these different parts of example 3 here, I'm also going to fill in the corresponding parts of the truth table for all conditional statements. So this is something that works for all conditional statements. P implies Q. So remember that we have different combinations here. We're going to see the different combinations here as we roll through this. So this is P, this is Q. In this part A, the first part, P, was true, and the second part, the conclusion, was also true, and we had, based on that, a true statement. Part B, you are a lawyer. Okay. So it looks like we have a matching hypothesis again, so that would be true. And then, you don't make $200 an hour, which might sound crazy, but a lot of lawyers, they make that. That's what they'll charge. A good lawyer, like this guy, instead of Mr. I think this is Lionel Hutz from The Simpsons, something like that. Not the best lawyer. He might not charge as much because of that. So you make $50 an hour. So the conclusion does not match with what I have up here. That would be false then. So if you are a lawyer, then you make $50 an hour. That does not jive with what I see up here. If I'm a lawyer, I'm supposed to make $200 an hour, not $50. This would be false. And so that's this second part of the second row here in my truth table. So I have true P and a false Q. That means the conditional statement, P implies Q, is also false, or is going to be false. Let's check out parts C and D here. If you are a doctor, that means this initial part is not true. The hypothesis is false. You make $200 an hour. Well, that's a true conclusion, but we didn't start with the same hypothesis. So I would say this is a true compared to what I had up here, but we didn't start off with the hypothesis being true. So this takes a little bit to wrap your mind around on this one, but we are saying this is actually a true statement. And we're saying that because we basically can't prove that it's false. And with conditional statements, if you can't prove something is false, then you assume it's true. So let's write that out as a little side note here. I'm going to use my different color for this side note, but I think very important that we write this down. So if the hypothesis is false, we can't say anything about the conclusion. So we assume the statement, the conditional statement, we assume the statement is true. So that is an important thing to remember with conditional statements. If you have a false hypothesis, one that doesn't match up with what you had started with, we assume the statement is true. So this one is false and then true, and with conditional statements, we assume that's true. In part D, you are a bum. Like this guy that said his family was kidnapped by ninjas and he needs money for karate lessons. You are a bum. At least he's creative, right? You make $75 an hour. $75 an hour? What the heck? Yeah, I read a story one time about a guy that pretended to be mentally handicapped in a wheelchair, made $100,000 a year doing that. So I think that just goes to show that, I don't know, it depends where your heart is. If you're going to give somebody money that's begging, it depends where your heart is. You can be doing the right thing and the other person can be doing the wrong thing and just cheating you out of your money. I feel personally better about like giving somebody food or helping them get a job, something like that, rather than just giving somebody money because of things like that, because I just don't know if I can trust them. But if you are a bum, so this is false hypothesis. This is not matching up with the hypothesis I started with, and then you make $75 an hour. That's a false conclusion, or it doesn't match up at least with the conclusion that we had here either. So I see false and false. That would be false here, crazy as this sounds, we say that's true based on the same reason we had talked about over here. So if the hypothesis is false, we can't say anything about the conclusion, so we assume the statement is true. So the truth table, the last little slot there, put a T there. And this matched up with part A, B, C, and D. But this truth table, this is for all conditional statements, not just these particular ones that we have here. And let's move on to another fresh new idea probably for a lot of you. Not this first line necessarily. So a conditional statement, we know about those. We've been learning about those in this lesson already. That's just the original statement. So I'm going to put that in parentheses because it's the idea that it's just the original. You're not going to change anything about it. And in symbols, general statements P and Q. This is P implies Q. And for an example, a relatively simple, quick to write example, if x equals 4, then 3x equals 12. So I'm just saying that's a conditional statement. I'm not saying whether it's true or not. Could we determine if it's true? Sure. We look at that, x equals 4, 3 times 4 would be 12. Yeah, that's a true statement. But we're not doing truth table values here yet, at least. Conditional. Next up is what you see over here. Perhaps you would like to switch your shoes to some good old Chuck Taylors, to some Converse shoes. So that helps me remember that this one, Converse, should be switch. That's the idea. We switch the statements. So I'm going to write Q implies P instead. So if we have x equals 4, then 3x equals 12, we switch those statements around. Now we would write if 3x equals 12, put that second part first, and we put the first part second. So then x equals 4. With the next one, this is called the inverse. And with the inverse, you negate. So I remember Converse, switching shoes to Converse, and then I remember the inverse is the other ones, the negation. So I go back to the original conditional statement and I negate both parts of that statement. So I say not P implies not Q. And if we look at our initial statement, I would just rewrite that with nots in there. So if x does not equal 4, then 3x does not equal 12. If there were nots in the original statement, then if we're going to negate it, we would actually take those nots out. We're not doing that here, but that's how that would work. It would be like a double negative would become a positive. And then finally, contrapositive. It sounds like the most complicated one, it's the longest word. It is the most complicated one, I guess you could say. You switch and negate. So we do both things. So we take P implies Q, we negate it, and we switch it around. So it would be not Q implies not P. So if I do that, I usually look at the converse. I rewrite the converse with nots in it. So if 3x does not equal 12, then x does not equal 3. And then I want to talk about something with the truth table values, something that we'll discover as we fill in the truth table here. So for any general statements, P and Q, you're going to have not P and not Q going here. You're going to have to write a little small for this one, but put conditional in this box. This is going to be P implies Q. Put in this box converse. This one is Q implies P. And then the inverse. This one, not P implies not Q. And finally the contrapositive. This is not Q implies not P. So filling out a truth table for these four related conditional statements. So we have our combinations from before. We have true, true, false, false, and true, false, true, false. That gets me all the possibilities, those four possibilities. For not P, good practice from lesson 2.2, the previous lesson, filling out these truth tables. I'll start and say truth tables again. Truth tables, I got this, just negating these two columns, making it the opposite in those two columns. So the conditional statement, P implies Q, we're going to go back to this momentarily here. So remember, if you have a false hypothesis, that automatically makes the conditional statement true. It doesn't matter what you have for the conclusion. The only time it's false is when you have a true hypothesis, a false conclusion. So that's really what we're looking for. Look for a true hypothesis and false conclusion. That's here to here. So this is the only one that's false. The rest of them are not like that. They're either true or false and whatever. All the rest of them then would be true. So again, for Q implies P, now go backwards. Look for the true to false one. That's right here. That's the only one that would be false. The rest would be true. Likewise, inverse for not P implies not Q. Now I'm going to look at these two columns. Look for the true to false one. That's this one to this one. That's the only false one. The rest are going to be true. And then same thing for the not Q to not P. Look for the true to false one. So here's the true to false for not P to not Q. And that was right here. I'm losing track of my place there. True to false, there we go. And then the rest of these would be true. So what do you notice about these columns here, these truth table values, right here and right here? If you look at those, aren't they the same? Yeah, they are. These two, I want you to connect these two. We'll go down towards the bottom. I want to leave a little space above that. And likewise, this one, this column, is the same as this column right here. So I'm going to have you connect those two as well. So conditional and contrapositive, and then converse and inverse, these are in pairs logically equivalent to each other. So these are logically equivalent. So it's important to remember that if you have a true conditional, you're going to have a true contrapositive. If you have a true converse, you're going to have a true inverse. If you have a false conditional, you're going to have a false contrapositive. And if you have a false converse, you're going to have a false inverse. These are logically equivalent because of that. So let's check out a final example where we use what we've just learned about conditionals and the related conditionals, converse, inverse, contrapositive, and we apply that to an actual statement here. So write the converse, inverse, and contrapositive of this statement. The statement is all squares are quadrilaterals. Then determine whether each statement is true or false. If a statement is false, give a counterexample. So the conditional, this is not in an if-then form right now, so I'm going to write it in an if-then form. So I could say I could go with if a figure is a square. I don't want to say if it is a square because it's too general at that point. You haven't described what it is. A figure, that's a better way to say it. So if something is a square, if a figure is a square, I suppose you could even say if a polygon is a square. But if a figure is a square, then now I can say it because I'm referring to a figure, then it is a quadrilateral. So let's think about that. Does that have to be true if a figure is a square? So like this, does that mean it has to be a quadrilateral? Yeah. A square is a four-sided shape and a quadrilateral is a four-sided shape as well. So this one is true. Only says if it's false to give a counterexample, so I'm filling that in. Don't have anything else to do for that one. Converse, we are switching the statements around. We are switching the P and the Q part. So now we're going to say if, and I can't say it is a quadrilateral. I'm going to go back to saying a figure to start. So if a figure is a quadrilateral, I think I have enough room to write quadrilateral up there, so I'm going to put it here. So if a figure is a quadrilateral, then it is a square. So does this have to be true? If you have a figure that is a quadrilateral, so it's a four-sided shape, doesn't specify anything beyond that, four-sided polygon, does it have to be a square? I would say no, definitely not. So this is false, but what makes it false? If it's false, you got to give a counterexample. So here's a counterexample. Here's actually a few counterexamples. You can see pictures of some counterexamples here. This is a quadrilateral, a trapezoid. However, it's not a square. A rhombus, that's a quadrilateral, but it's not a square. Rectangle, quadrilateral, not a square. We could list any one of those things other than square as counterexamples. So I could say a kite, I could say a rhombus, I could say a trapezoid, I could say more things than that. So I'll write etc. there. If it says give a counterexample, you really only would have to give one, but I'm giving you multiple options there. Inverse, now we take the original statement and we negate it. So we're going to not flip things around, we just put nots in there. So we would say something like if a figure is not or isn't, both would work. I'll go with is not. So if a figure is not a square, then it is not a quadrilateral. So if a figure is not a square, okay, I could pick kite, I could pick rhombus, I could pick a pentagon if I wanted to. If a figure is not a square, then it is not a quadrilateral. Well, I've got some shapes there that are not squares but are quadrilaterals, so that would also be a false statement. And notice, that these were logically equivalent, so you should get the same answer. Remember from our truth table back here that converse and inverse are logically equivalent. So we should expect to get false if this was false. So some counterexamples, we could say the same thing for counterexamples. I don't have to come up with new ones, they're already there. So let's draw a couple little arrows like that. So these are some valid counterexamples. And contrapositive, we should expect it to be what? If this is true and conditional and contrapositive are logically equivalent, we should expect it to be true. So let's find out if that's the case. So if, now we're switching and negating. So I'm going to start with the converse and put nots in there. If a figure is not a quadrilateral, then it is not a square. So a figure that's not a quadrilateral, so a shape or a polygon that does not have four sides, pentagon, hexagon, heptagon, triangle, a segment, a point, then it is not a square. None of those things are going to be squares. If you have something that's not a quadrilateral, it cannot be a square. So this would be a true statement as well. And that will do it for this lesson. That's 2.3 in a nutshell. Make sure you check out the Appalachian Trail, Jennifer Farrar Davis's books. She's a good writer too, so I would say buy those books if you're interested in that story. This terminology, once again, make sure you know that now that we've gone through the whole lesson. If you understand what all those things are, you should be pretty confident in your ability to do these problems on your own. All right, that'll do it, and I'll see you later for our next lesson.